Welcome back, everyone. And today we're going to continue off where we left off last time. Last time we created Bezier curves, like a very simple curve with just 4 points. Today we're going to go further. We're going to actually combine a bunch of Bezier curves and make a spline out of it. And then we're going to kind of really work on building an editor tool for it too. Because once you start building engines, one of the things you kind of start needing to do is build tools that you can use to kind of modify things and save its data. So today we're just going to start putting together our first editor object to handle a lot of our changes, our spline, really, to mainly manage our spline. So let's quickly go do some core changes that are needed for this week's lesson. So we're going to go to the core. Let me scroll back to straight to the top. One of the first changes we're going to be doing is to our renderable class, and we're going to do a change here on this line where we assign our material. Originally, we would just bring in the material; it was required. And now we're checking to see if it's null or undefined. So this way we can not have to create a renderable with a material right off the bat. I wanted to be able to create a renderable, then apply a material later. So that's what that change is for. Another change is to its draw event or draw function. I started to realize that maybe the renderable should handle the binding of its vertex array. So we're applying it here, and we're actually going to remove it from our renderable, our render object. So in our draw, we're going to load up our VAO. So that's our renderable. We're going to do a couple of changes to our vec3 because I had to do a lot of things. One of them is we're going to check the arguments. These two lines of code are new. And if the arguments are 3, we're going to apply the values to the vec3. So in case we pass in an array or another vec3, we're basically going to create a new vec3 cloning the data inside that array or vec3. So that's that. Another change I did was really to our mathematical functions. In multi and add, I added an out. So this way we can do non-destructive changes, kind of. So instead of me just passing the value and then modifying this object, I want to use this object with the values, but return back a value outside. Maybe I want if I'm doing a lot of looping, I'd rather just create one object and just update that object instead of modifying this object. So we're just creating an out thing. So if out is defined, we use out. If out is not defined, it uses this. So there we go. And I do check, is out equal to this, then modify. Because if out is not this, then this object has not been updated. So the same thing goes for add. And we added a new function called sub because we need to do some subtraction with vec3s, and follows the new theme as well. So that is our vec3 changes. I think that's all the changes I did for vec3. Yep. I kind of pre-open everything and put new comments. I think one of the last big changes is how frame per second counter was working. Apparently the way I was doing it is not the most efficient, not necessarily the most efficient, the most accurate way of doing it. I was doing it by dividing one by the time it took to create the previous frame. And apparently that can kind of create incorrect values. Since then, I've learned that the best option to really do a counter is to really just count how many frames and then update the value every second. So if a second of time has passed, just update that value. So you'll see how it works here. So we're gonna have 2 new variables we're adding. This keeps track of the last time, the date, the last time the FPS was reported. and FPS count is just a constant count of how many frames have already passed since that last FPS report. So 2 new variables. We're going to, this new line kind of just saves the now into our FPS last and last frame. We still need last frame and other for other things. So I was using that for the FPS, now I'm not, because they need to be treated differently. So that's the start. This hasn't changed really. And the really big change is this part. So we're just, like I said, we're just going to count the FPS. We're going to use our current and subtract it with our last FPS. If it's equal to or greater than 1,000 milliseconds, basically 1 second has elapsed since the last time reported. We just report it. We just put that value into our FPS counter, that we public value. Reset our counter and set last to our current date and time, or our current tick, if you want to call it. I think that's what Linux calls it. I think call them ticks. How many milliseconds since the dawn of time? So this way we get a more accurate FPS counter. So that should make things you're able to see the value, what's actually going on, because this now, because start to realize now, like certain times it would go up to like 70 frames per second, and I know a WebGL can't go past 60, I believe. So I knew there was something wrong. So as I researched further, is that some people make the mistake I made by using that division, and this is really the only accurate way of doing an FPS counter. So that is that. And then the last big change is here to our render object inside our prepare next. Just get rid of binding the VAL. Like I said, now the renderer, or the renderable object, is going to bind it on draw. All right, so those are the quick changes. Now we're going to go to Spline. Spline, in a previous lesson, we had the Bezier curve, or the Bezier object, and we had the drag points object. The Bezier object features have been put into a new class called Spline, and a lot of our drag point features has been put into Spline editor. The Bezier pretty much just held 2 functions. It's just really get point and generate. Our new Spline object does a lot more than that. I'll go into more detail in a minute. So let's go to the very top, because I did some changes to our picking object. I'm trying to make the picking object a lot more generalized. So this way it's more reusable compared to the last change, because last lesson we introduced the new picking object to try to facilitate picking, and the way I went about it was good but not good enough. So now in this new implementation, we're not going to deal with the actual objects data that we're tracking, because if I'm tracking a bunch of different type of objects, they might not have a position or something else, or I might need to treat it slightly differently. So we're not tracking that anymore. So one of the big changes is our reference, a register object class, or sorry, register function. Originally we brought in an object and our callback. We're not bringing the object anymore, so I commented out, I moved it over here. So we still have our ID, and I renamed this from callback to callback object. So now we're going to have to pass in an object that has at least 2 events. I think unpicking down and unpicking move. So that's that. So that's our register. And I think the only other change is ID to color, which brings in this A value, which is like our out value, really. So if A is null or undefined, it creates a float 32 array, and then updates the value and returns that. So this way I can kind of just create one variable and reuse it in a loop without having constantly to create a new float32 array repeatedly. You know, like it's efficient just to reuse variables that pre-exist in memory than to recreate them in a loop. And you got to remember, when we're rendering frames, we're doing a lot of looping. So any little fat we can cut out, the better. So ID to color got updated. On mouse down, now we're going to call our callback objects on picking down event. We're still going to keep track of our initial data, and then and we comment out this thing because we're not dealing with the objects anymore. The picking handler just handles the mouse position and its delta. That's all it does now. Like, here's an example of that. And on mouse move, I got rid of this and all this other stuff. I even call it a hack because I was treating things differently that shouldn't be treated that way in this object. So all this stuff now it lives in the callback objects on picking move. So the only thing we're going to keep track of is our initial position and the delta since we moved. And we just pass that information and plus the target ID that's been picked. That's it. Yep. Target. Okay. So yeah, when this handler runs, it sets the target. That's right. That's where on down event does that. I was like, wait a minute, where's the target set? Yeah, that's right. Target set over here. Okay. So that's our picking object. We're done with that. Those are the changes for that. The only change I did to dynamic mesh is since I have its own draw event class, or I'm replacing the draw function for our renderable. I gotta bind the VAO manually. So that's about it. So dynamic class. So now we're going to the meat and potatoes of today's lesson is the spline object and the spline editor. Now, the reason why I have a spline and spline editor is that spline is actually spline data. That's all it does. All it does is handle the array of positions of all the points that determines a spline and basically how to traverse the spline. The reason why I want the object to be separate, like I think in the previous lesson, the data was actually part of drag points. Drag points had the editor tools and the data. The editor tools should be separate because if we're gonna make a game object and we're gonna do a final output for like an actual game, we don't want to include Spline, all the editing tools. Anything related to editing shouldn't be in the final output of a game or an app. These are just tools to help us set up our scene, set up our paths, whatever. Whatever the tool function is to do is to help us get the game ready to actually be useful. So the idea is that spine data and spine editor are two separate objects, and spine editor kind of just uses that data. It manipulates it, it changes it, it does what it does. And hopefully at the very end, at some point, spline editor or maybe spline itself will actually save the data somewhere and allows us to reload the data. So probably this object is going to be saving and loading. So this way, we create a spline, we have all the positions perfectly, then we do a save, and then next time when we come around, we can load it. That functionality doesn't exist, but I'm moving toward that that thing. So splines are going to manage the data and probably also how to animate through the spline. So let's open this up. So the spline, we have a constructor. So this is going to be our points. And we pass in our curve count. The curve count is how many Bezier curves do we want the spline to have. So by default, it's just going to be 1. And then all this thing does is create all the points to create that many curves per Bezier. A lot of this math, it's not scary. The only thing I'm doing is just, how many for every curve there's 3 points generally plus one more, and then I'm using that as like a whole 1 unit. So every point is 1 unit away from each other. So I'm going to use the total points as 1 unit apart, and then I'm multiplying by negative 0.05. Well, technically what I'm doing here is really dividing by 2, because I want to bring it, I want to center it on the origin. When I'm creating it, I want the spline to be centered on the origin. And reason why I'm not doing division by 2 and more doing multiplication by 0.5 is because apparently, GPU wise, multiplication is less intensive than division. So multiplication by 0.5 is, I guess, more optimized than doing a division by 2. So, and I need a negative anyway. So this way the starting position is on the negative side of the x-axis. So that explains that. And based on the point, so if we're on a position point or an anchor, I want the y to be different. So all of our position points, the red dots, that our main points, is going to have a modulus of 0. So that's always going to be flat right on the line. And then our points are going to be either 1 or negative 1. They're going to be up and down. So this way we create a nice, by default, we will create a nice sine wave. And then we just add it. So that's what's happening in the constructor. We have a function that just gives us a total count of curves. And it's just length minus 1 times divided by 3. So this way we, we have even though we have like an array full of vec3s, this way we can determine how many curves we are based on how many points. And cubic Bezier point is the same function as our Bezier get point. It's the same function. I just renamed it to cubic Bezier point because that's what this gives me, and it's a static. So when you make an instance of Spline, this object is not brought into that object. We only need to use it because at some point there's going to be like an animated thing. An animated function will actually use that. Okay, so that's the Spline data. It's very bare bones. Like I said, that's all it's meant to do, is really just to hold the data in there, and hopefully in the future help you just how to step through it, how to do things like that. Now we got our Spline editor. There's been some small changes to the shader. I just can't remember what it was. It's just small little changes. So I'll just leave this on the screen. If you guys are just quickly typing away, just pause it, or you just go to GitHub and just copy and paste. It's just a couple of small changes here and there, because I'm trying to use one shader to render everything. The editor object renders the whole thing. I'm not even using the debugger debug line tool to create the lines. The Spline editor was going to handle all rendering. So that's the shader. We might have a thing that colors might be new. So setting up some default colors. And we'll create our shader, create our material. So our render editor is also a renderable. Do I extend it? No, I don't extend it. I just use objects that are. I just use, I have it just a draw event and position, I guess, or something. Do I have position? No, I don't. Okay. And this, it knows not to use the model matrix. So I set up so it doesn't use the model matrix because this thing does not actually have a model. This, like I said, this just manages the data of Spline in basically world units. All right, so that's our renderable. So our draw function, we have a draw function. I'd put it on the top because I don't know. I should go to the constructor for it, but since we're here, this is our new draw function. It binds it. Like remember, all our renderables have to bind the VAO now. I think this is the reason why I made that change, because I want this object to do 3 things at once. You know what? Let me do the constructor first, because some things here you might not realize what's going on. So here's our constructor. We're going to pass in our sample size and our spline. So the data that we're using, and between our main points, how many samples are we going to do to create the curve? So you can define how many samples. I have a lot of comments. So there's data, our move rate, pick list. We're going to keep track of all the points that are draggable. Hence why we have the unpicking move and unpicking down. So we can kind of track. So this object tracks its own draggable items and then drags it. Hence why it's called an editor object, because this is really just a UI component. Our editor is a 3-dimensional UI component. So we're going to keep track of all the points in the spline. So we're going to just loop through the spline and turn all the points of data into draggable items. Pick target. Every time you pick a point, you're not going to move just that point anymore. We have a bunch of constraints based on what kind of point it is. So if I pick one of the main points, like one of the position points, and you drag it around, it's also going to drag its anchor points that allows you to change the curve. So this way you don't drag the points, the main point, and then the anchors kind of get stayed where they are. So that's why I have a target of array of 3 spots. Depending on what you pick, I might only be moving 1 object, 2, or up to 3 objects. So this thing just keeps track of once you click on a dot, how many dots are we actually going to move? Because like I said, we're going to end up moving more than just 1 dot for every time you select and move something. And if you move the anchor, you're also going to move the other anchor, because one side is going to be is going to have a constraint to the other side, and we have 2 types of constraints we can use. I don't have anything to kind of let you switch back and forth, but I'm going to show you both, and I'm just going to leave one commented out. And these are just reusable vex, because I'm going to use this a lot. And there's another reason why I have an array, but I'll show you in a little bit. We're going to save the color dots that we're going to color, and then our connections. I really need rename these, but those are just 2 different colors. We're going to change the value in our draw event. So now we're going to create the points and our buffers for the GPU, so that we can take our spline data and make something that we can render and see on screen. So we're going to render our UI component. I'm just going through the spline points and then creating flat float 32 arrays out of them. So I'm just creating the verts. The color, depending on which point it is, I'm using index 1 or 2, because we're going to have 3 colors. So if I'm rendering the dots, I'm going to push these 3 colors to the shader. So I'm telling you, so here in colors, I'm just saying, okay, well, we're going to use index 1 or index 2. So this is the red and this is green. These are going to be the 2 color points. And I put gray in there by default, so I don't have to do 3. So by default, one of the things are going to render automatically to 0, which is blue. There's going to be the actual curve line. It's going to be in blue. And the connection lines are in gray. So now that we set up the color for each dot, we got to create our color ID. So this way we can identify it by using our picking object and using our custom frame buffer object. So once we got that, then we add a bunch of our data to our pick list. So we create a struct, and we have our ID. We save it. Is it a connection? I should probably say is anchor, but the anchor is the thing that actually modifies the curve and not the actual position points. Vec byte start. Now the thing is I need to know for this dot where in the byte buffer does it begin. So this is basically our byte buffer that we're building, and I want to know exactly where in the byte buffer the position starts. So when I do a sub buffer update, this is the value that will tell me where to start. Position is just the spline position data. So we can, when we're dragging, we can reference the actual spline data and modify the spline data directly. And then initial pose is what the picking object used to handle before, the starting position when you do a mouse down. So this, our pick list kind of manages all that. Since we got the constructor out of the way, now that you know what certain, did I build the buffer yet? Oh, sorry, I didn't even finish. I'm sorry. All right, so now that we're done with the loop, we have all our data. Now we create our VAO. So we have our float array buffer, which we put in our verts, our ID, and our colors. This is a 3 float, and this one is a single float array. So because we're just passing in the color index, and I know I usually put the color index in vert and make it 4, but I don't want to complicate the vert buffer array because we need to update. The way I want to do the updating, I need to keep just vert information in that buffer. So I need that W state. It can't be there. It'll actually just complicate doing the sub buffer update. So that's the reason why I'm keeping color in its own separate buffer. Then we finalize the VAO. We do our vert count. So this way, good. Now we're going to use dynamic mesh to create our curve mesh, which is the curve mesh. Which one's that? Line curves. So this is all the lines that generate the curve, the samples. So our dynamic mesh, at some point it has a default size. So at some point maybe we may have to make it larger or smaller or more dynamic. But for now it holds 100 verts. So it's an array of 300 floats. If I remember how that works, it's just how many vertices are you going to use. And our line mesh is the line connectors, the gray lines, and our line mesh draw mode is just lines. So that's that. And then when we go back up here, we go to draw. We bind our VAO to draw our dots. We set our uniform color to use the dot colors, and then we just draw. And then originally, like I said, I was binding it, but then I changed it. Remember, the renderables now bind the VAO in the draw function. So this will simplify things. So instead of me doing a lot of binding here and here, the draw function handles it. So this is the reason why I did that change to the core, because it makes more sense at this point in time that the renderer handles that aspect of rendering. And when we draw connectors, we change our U colors again to using the connection color, which just adds that gray color. All right. Let's not talk about this one yet. This one happens at the end. We have our picking down. So now that we're picking, we're going to go look at our pick list and find the dot that's being moved. And at this point, we're going to figure out the starting and ending point of because let's say if it's the center point, I want to get the previous anchor and the next anchor. I call it connections. I went back and started renaming everything from connection to anchors. So if I grab the center point, I want the anchor on the left and the anchor on the right. So I'm getting the starting and ending position of the data, and I'm setting the pick target mode to 0. So I know I'm moving a position, so I know which constraints to use when I'm dragging things around. If you selected the right anchor, the starting position is this, and the ending position is I. If you're doing the left anchor, the starting position is I, and the left is that. So all this is just compensates what the next dot after the center is, because in case the center, it's the last position and then the anchor after that. So that's just determines where in this huge array we're gonna slice, because we want those 2 to 3 vertices that we want to move. And then in here in the loop, we just loop it. We're just gonna update the information for that, and create our pick target. So we're gonna loop from the starting, loop till we reach the end of our slice, and loop. And we set the target in that array. Remember, it was 3 nulls. And we set up our initial. We copy the position that it currently exists in our spline data. And then at the very end, we do f size. If you ever did like byte streaming, you might always create a buffer of let's say if you're streaming, if you're writing streaming stuff like coding, you have a byte array. Let's say you have a byte array of like 100 bytes, and when you do a fill, say okay, fill data, and here's my byte array of 100. Usually it will fill up the byte array and tell you how much it has filled. So let's say if you do it, you're streaming data from the server, and it only sent you 50 bytes of data. So it's going to take that 100 byte array, fill in the first 50, and tell you it's 50. So that's what f size is. It's just how much of this array am I actually filling in. So if I'm only filling in 2 points, I want to know that when I'm processing the data on the move event, that I only want to access the positions, the index 0 and 1, because that's 2 data. That's just 2 things that have been modified. Basically, yeah, how many have been picked for moving. Now we go to our unpick move. Our unpick move looks very big and very scary, but that's because there's a lot of comments. If I took a lot of the comments out, it's no big deal. And it's the same thing from our previous. It's a lot of the same stuff, except I have more constraints now. So to start off with, we are going to calculate the offset position. So we set our value to 0. We get our camera left. We use our delta and our move rate. How much movement has moved from our delta x and delta y is the amount of movement since our last frame from the initial position. P is just our reusable position. It's just mapping the data from like a we're mapping the value. I'm trying to explain this, because the index of this is 0, 1, 2, 3, but for each item in the array, there's actually 3 vertices. So that's really what P is. It just helps me target things. I probably explained it myself right here. Mapping the index of the target array to what works for the subbuffer array. Haha. See, I love that comment things to make sure I understand it. And then in case I forget, there it is. It's explaining everything to me. So all this code really commenting really helps you guys out as well as it helps me. So if we're in picking mode, that means we got the main position. There's one thing you should realize. When we're looping, we're going to loop through all our targets. If we're in mode 1, we're going to update each one. There's 2 things. If we're in mode 0, which we're moving the main point, that means our center point plus our 2 anchors or 1 anchor, depending if you're an endpoint, they all move by the exact same offset. So that's what we're doing. So we're looping through, and we're going to update it. If the target mode is equal to 0, and the f size is equal to 2, and its ID, then we also do it. This whole chunk means if it's an endpoint and there's only one anchor and the thing we actually picked is the anchor, we just move the anchor only. So we're only going to move that one small piece of data. We're not moving anything else. So when we're looping through our anchors, those are the two conditions. If we're 0, we're going to update all of them, the anchors and the center point. Else, if we're in anchor mode, that we're dragging anchor, we're only going to move the anchor only if it's the only anchor and the current one that we're looping through is the one we selected. That's why it's size 2, because if it's an endpoint, we're only going to get back 2 targets. If it's anything that lives in between, it will actually return back 3 targets. It will have a left and a right, or a previous and next anchor. And then when we loop through, we just kind of just save our data, and our data here is the size of the amount of anchors we have, how many points we're moving. So we're kind of creating an array of how big the data is, and then we just save that. This is what we're going to save to our subbuffer. Now, in the event that it's a target of 0, mode of 1, that means we're moving an anchor, but we have 2 anchors to move, and the loop is at 0. It's very complicated because we have to apply constraints. So even though we're going to loop 3 times, we're going to update all the data on the first loop, and then the remaining loops that go through will actually just store all the changes for our subbuffer thing. So the first thing we're going to do, if we're actually dragging our 2 anchors, we want to know which one is the main anchor. Because when we move one anchor, we're going to have 2 constraints. We have a mirror constraint, and we have mirror angle only constraint. So this way, if I move one point in the mirror, I want the other point to be the exact opposite. So they're perfectly in line. They're perfect inverts of each other. So if this goes in the positive direction, this thing goes in the negative direction at the exact same angle. So that's a mirror constraint. A mirror angle only constraint is that everything moves in the same angle, but the distance from the center can vary. So point A can be 50 units away, and the other one could be 2 units away. But they have to have invert angles that are the same or opposites of each other. So they're perfectly sort of like a mirror, almost mirror images, except their heights are different. So that's basically what we do. So like I said, there's 2 constraints. We're going to do a mirror where the angle and its height, its distance are equal, and the other constraint is just their angles are the same, but their distance can be different. They're independent. So the first thing is we're going to move the main anchor that we're actually dragging first. We update its data. Then we do, get delta from center point to new position. We're going to use the center point as our origin because this thing lives in world space. So we have to use the center point as the origin, as a starting point to do a lot of our math. So we just get the delta from there. And if we're just doing a simple mirror, angle and distance, all we have to do is just our delta plus our origin, and then just copy it into the B anchor. Now, let me explain this, because I screwed this up, and it took me a while to realize how to do this correctly. Target 1 is the center point. It's always going to be the center point, especially when you're dealing with 3. That means 0 is the left side, 1 is the center, and 2 is the right side. So when I show you visually, you'll see. So the center point will always be 0. Now, if I want to find the distance from the anchor to the center point, normally you would do anchor minus the center point or origin. That gives you the distance or the exact delta from the origin to that. It's like how much movement in the 3 axes does it take to get from the origin to this position? This one, I'm doing the exact opposite. I'm taking the origin and subtracting our actual anchor that we're moving. So this way, I get the inverse delta. So if I take this inverse delta and then add it to our origin, I then go to the exact opposite angle and direction that we're dragging the main anchor in. So it's just like order of operations. If I were to do it the exact opposite, where I subtract, if I move pick temp pose over here and then pick target over there, and do the exact, then our second anchor would be in the exact same position as our first anchor. So by swapping the values, the order of operation of our subtraction, we go from making an exact copy of the delta needed to get to the new position to making an invert value of that. So this way we have the exact opposite position that it needs to be from our center origin. So I just want to explain that little math because I screwed myself up and it took me a while to realize to swap it. That things were in odd positions. And that's that. Then at the very end, I'll explain this when I comment this out later. We save our data, then we use update array buff sub data, whatever. We pass in our buffer. Remember I said like this thing tells me, so I take the first anchor and tell me it's vec byte start, and then I pass in the data. Now, you might be asking why I'm doing this, and I actually did this about 2 or 3 times, and I kept optimizing it. So originally what I did was, for every anchor that I'm moving, I did a subbuffer update. So that means if at most I'm modifying the subbuffer 3 times. I'm calling it 3 times for every dot that I'm moving. Because remember, like I said, when we move 1 dot, we're going to be moving 2 or 3 dots in all honesty. So I'm going to call the GPU 3 times for every time there's a mouse movement. That's very wasteful. So the idea is that if I collect the 3 and keep them in sequential, like that's the key thing. They are in sequential. They have to be sequential for this to work. So when I generated the buffer and created the data array for it, I built it in the exact has to be built in the exact same order that exists in the drag list, in the picking list. So this way, so if I'm moving vertices 2, 3, and 4, and they're in the exact order in like the buffer array, all I need to do is get the starting position of our first vertice, and then just pull in all the data for the 3 verts, and it'll update all 3. So in the event that we're doing the first dragging event, like we're dragging the main point and the 2 anchors follow the center point, we need to update all 3 data, all 3 points of data, all 3 vertices. If we're dragging an anchor, let's say if we're just dragging an end anchor, we're going to be updating the anchor and the center point. But the center point data doesn't change. But because of the way it's built, I'm updating 2 vertices instead of 1. But at the end of the day, I'm still just doing 1 call to the GPU. And in an instance that we're doing 3, we have 3 points that are being modified. The 2 anchors are changing, but the center point isn't. But we're still sending the data for all 3 vertices and updating it. So the whole idea is to minimize as many possible calls to the GPU as possible, and that's why I did it this way. I hope I'm explaining this correctly. I'm just, like I said, like the array on the GPU, you think about all our vertices on the GPU, and I just want to update 2, 3, and 4, and that's it. And that's the section. Instead of updating 2, updating 3, and updating 4, I'm going to do it all in one go. So I'm taking a slice of that our data array and then plopping it into the GPU. And like I said, the only wasteful thing is that the center point gets updated even though there's no change to it. But this is to make sure that we don't call the GPU more than once. So I think it's better to pass in 3 extra floats of information than to call the GPU twice. So if we call it once, but 3 extra bits of information, 3 extra floats, is more efficient than calling the GPU 2 or 3 times. So that is the rationale behind the way this editor is built, and why it goes through this weird loop, and why I have a target of 3. And like I said, everything has to be in sequential. All right, so now I'm explaining this insanity. I wish I should maybe find some way to illustrate it. I don't know. But when all said and done, and our GPU has been updated, now we're going to update our dynamic mesh, which then goes up here. We don't need picking down anymore. And the only thing it does is takes all our spline data and updates our curve. So it clears out our curve mesh, the actual curve that we're drawing, and the line connectors, and just rebuilding the data, and then pushing it to the GPU. So we're going to do what we do first. So every time you drag, we're actually going to redraw the spline. This function can use a lot more optimization because I'm updating the entire buffer instead of just a slice of it. So I can actually go further and do the same thing here and only modify a slice of the buffer. But at this point, I'm being lazy. So this one is not as optimized as it could be. I think as I need to update, I have to create dynamic mesh with functionality to do updating slices of information. But yeah, so just keep in mind when I'm moving the dots, it's as optimized as possible. But when I'm actually creating the curves and the lines, I'm not very optimized. I am only doing 2 calls to the GPU, the line and the curves. I'm only doing 2 calls, but I'm updating the entire mesh instead of just a chunk of the mesh, which would be more efficient to just, if I only need to update 10 vertices instead of 40, it'd be better just to do those 10 vertices only and not waste so much time. And because I'm wasting time updating all 40 vertices and then pushing it to the GPU. So I just want to say update dynamic mesh is not very optimized, but it gets the job done. So I have like 2 ways of doing it: the not optimized way, and then the other one is very optimized. And you can tell the other one looks more complicated because it's taking that extra steps of optimization, and this one is not. So it's very simple. And that's it. And that is the end of our spline. Now, oh my God, I don't know. Oh boy. Now if we go to our test, in our prepare, we had all those prepare things. Now this is the only prepare we need. We prepare our spline, we prepare our editor, and the editor gets pushed into our scene. And that's that. Now if we go back to here, here's what you would see. And like I said, we're building the anchors. And I'm lazy, like I didn't create like an initial renderer. So it only starts rendering the data when you start dragging something. So as you can see, these are our end position points, and these are our end anchor points. And when I move, get that just right, our position, it moves our anchor. So that is that constraint in mode 0. So if I move this, it moves the anchor with it. So let's go to 4 curves. We want 4 curves merged together. So we refresh. Now we have all these points, tons of points. So here's our endpoint. And here is, let me just do it together. Here is our one of our anchor points. As you can see, the constraint, if I move one, it's going to move the other. And this is that simple constraint, just that mirror constraint. So, and you know, like, and we move the points. You know, it can. So this way, it works and functions how you expect it, especially from if you ever did vector art or dealt with vectors before, like a vector editor like Inkscape or Illustrator. This is what you expect these path tools to work. You know, they have different constraints that you can modify. This way, you can create your curve. So when we have a mirror thing, we can create really smooth curves, and it's like perfectly smooth. And here's our 3-dimensional curve. So let me convert this down to 3, so we have so many points to deal with. And I'm going to go back to Spline, and I'm going to use the other one. So I'm going to go back to, let me see, what's the name of this function? So you guys know, unpicking move. So after I got the delta, this is the line that creates our mirror, but we don't need this anymore. Now I want to do the other constraint. So I'm going to take this, drag it over here, do a save. So to do a mirror constraint with just the angle, we need to get the magnitude of our second anchor. So by using our center as a position, as our origin, we're going to use its magnitude function to and then we're going to pass in our anchor to get the distance between the center point to the anchor. Now, since we have our delta, the first thing we need to do is normalize it. So we normalize the data, our delta, then we multiply. So once we have it normalized, we can easily multiply our distance or magnitude. So we normalize, we multiply by our distance, and then we add our origin. Just like up here, we delta and we add our center origin. So we add our center origin and then B2 position copy delta. So these 3 lines of code allows us to keep the exact same angle, but to keep the distances different. Independent, I guess, should be the right word. So if we go back here and refresh, and I start dragging, let me see if I can drag these in a nice way. As you can see, this one point goes really far, and this point I can draw very, very close. It looks like it's going far, but it's just the angle of view. So this angle is much better. So as you can see now, the angle is being mirrored. So they're exact mirror of each other when it comes to its angle. But with that change of constraint is we can keep the distances independent of each other. So instead of making really smooth curve like a normal mirror would do, I can do kind of a curve like this, kind of like a sharp turn. And I can make the turn even sharper by getting it closer. So if we're doing animations, it's going to be like a very sharp turn and then around. And that's it. So we have 2 constraints. And the only last thing I didn't put in there is just have these 2 points to be completely independent of each other. No constraints whatsoever. So this point and this point moves independently of each other. So you can actually make even crazier curves with that kind of constraint. But I haven't built that in. And that's like an easier one because it's just no constraints at all. You just have to, I guess, put an if statement that that just updates. It's the same like this thing. Like this point has that if statement that goes with mode 0. It just runs it independently. So this one's kind of like, since it's an endpoint, it's not connected to something else that constrains it. it just moves independently. And that is it. And like I said, we have those constraints that it moves, the center point moves the anchors with it. And we create a wacky 3D shape. And there's our wacky shape. In the next lesson, I am going to start working on animating. I want to have a cube that moves on this curve. So, and I want it to be dynamic. So as we're modifying the curve, we will actually in real time have the cube move on the curve as we move it. So it will look really cool. I've done it in 2D before, so I'm just going to do it in 3D. So basically, congratulations for building your first 3-dimensional UI component, because this is what this really is. This is a UI component. This is what you would see in a vector drawing application, but this is done in 3D space. So your curves are crazy. They can be anywhere and everywhere. Down the line, when fungi gets more fleshed out and we have more editor type of foundation, maybe I'll revisit this and allow us to apply we can change the constraints per point. So if I pick this point, I say I want to have a mirror constraint, and maybe this point will have a mirror angle mirror only constraint. So this way you can really customize the curve instead of having one for all type of thing that right now it's kind of hard coded. But in the future we can make this even better. But like I said, baby steps. To build these things, you got it's little by little, because there's a lot of foundation that needs to be built to do it. Like it took us a long time to get us to a point where we have a pretty good picking object. And it's not the end picking object either, because we're using frame buffers. And down the future, we're going to use raycasting to determine which points we're dragging, and that will be our main way of determining what's selected and what's moving. So for now, this is how it is. That's it. The only last thing I want to mention is that in some of the previous lessons, I was planning on rewriting fungi for the desktop using OpenGL 4 and Golang. After I did a bunch of research, I decided to change direction of fungi for the desktop. I really want to get into augmented reality, and Windows holographic is the main thing for Windows. Really, the only real augmented reality framework or whatever tools or hardware that you can really get, that the real good stuff, the stuff you put on it and you actually see things, not like phone AR. Phone AR is kind of fake because you're looking through a camera and not actually through like a clear piece of glass like a HoloLens is. And for the most part, I've always known that you had to use Unity to write 3D software for HoloLens. And I would lately I've been thinking, I don't want to use Unity. I would like to make fungi work on HoloLens. So I went to research is like, how can I build 3D software for HoloLens without Unity? And apparently there's official tutorials on how to use DirectX to kind of, and apparently there's a lot of the example apps that were built in the very beginning were DirectX apps, and DirectX is kind of it's similar-ish. Like I don't know it very well at all. So, but I looked at one tutorial on how to create a triangle, and for the most part is no more complicated than WebGL or OpenGL. It follows a lot the same rules. And in all honesty, OpenGL on Windows and WebGL on Windows actually is just an abstract layer for DirectX. So anything so a lot of what we're doing, it's kind of an extension of DirectX by what I've read so far. So that is probably the direction I am going to go officially now, that I'm actually going to use C#, Visual Studio, and DirectX to rebuild fungi on the desktop in the hopes of using it as HoloLens graphics and game engine. And in the end of the day, it can be used as in a desktop game engine. It doesn't have to work for HoloLens in general. It's just I would like to be able to do this without Unity. And like I said, I really want to be an augmented reality developer. Foremost, in the next 2 years, that's where the technology is really going to be once HoloLens is released. And magically, there's like 2 or 3 other competitors that have HoloLens type equipment with better field of view. And Windows Holographic is the framework that everything works at. So maybe once I start building it, maybe I can do a fund me to help me buy a HoloLens for testing, or I don't need to buy a HoloLens because the VR compatible Holo headsets are coming out in August. They're only $300, so I don't need $3,000 to really just start developing in it, since I can't really use it for at least the next 1 or 2 years when HoloLens actually comes out. So it's like a 1 or 2 year wait to actually get to the augmented reality that I want to do. So that's plenty of time for me to learn DirectX and build Fungi. I wish I'm probably going to call it Fungi X or Fungi DX as the DX version. And I really do want to do the OpenGL Golang, because I like the idea of learning Golang. The Go language is, I like it the way it's built. It's complicated yet very much more simpler. I like how it goes. I am a very functional programmer, even though I do use object oriented a lot. I still do like functional programming. And Golang makes it impossible to do anything but functional programming. So that will help me get better at that style of programming. Because if I'm in the object-oriented language, I'll probably will use its features since it's there. Why not use it, right? There's no point in doing functional programming in an object-oriented language. Sometimes it's hard to do it, so you kind of have no choice unless you want to spend more time jumping through loops to do certain things. So yeah, that's it. So I don't know if you guys are interested in learning DirectX. If you guys are, maybe I'll make, as I'm building that, I'll make a YouTube tutorial. It'll be similar to this, except to be using Visual Studio. And that be it. I think it's about an hour, whatever. Like, subscribe. I hope you learned something. Have any questions? Comment. I really reply to everyone that when I can. And yeah, have fun. See you guys in the next lesson. Click.